3, 2, 1. Relax.
Hi everyone, I'm David Greenberg. This is episode 30 of Machine Learning and Hereon Looking to the Black Box. We're going to have an interesting paper presented by Vadim Zinchenko, master's student in our group. So we've seen a lot of different applications of machine learning, in particular deep learning. We've seen neural networks calculate the physics for parameterizations and climate and weather models. We've seen them make predictions of weather. We've seen them solve differential equations. They can do all this amazing stuff, and the scale and the speed and the accuracy with which they do this stuff is increasing all the time. What's not increasing so much, especially as these networks get bigger and more complicated to train and use, is our understanding of how they work, of why they do what they do. This is a really important task in our science, trying to explain why your model predicts something. This is difficult even when your model is physical and interpretable, and it can be even more difficult for machine learning. But there are approaches, and we're going to hear about some of them in this paper. So Vadim, with that, I will turn it over to you.
Thank you, David, for this nice introduction. Well, hello, everybody. Today, we are going to make the black box a bit more transparent with help of Benjamin Toms, Elizabeth Barnes, and Imer Uphoff. I'm very sorry if I didn't pronounce it correct. And we are going to discuss their paper, Physically Interpretable Neural Networks for the Geosciences Applications to Earth System Variability. And here they show two methods. Those could be used for neural network interpretation. It's backward optimization and layerwise relevance propagation. Both of these methods are based on backward propagation of the neural network output or losses into the input layer. And they strongly emphasize that that the interpretation of the network is important not only just for understanding how it works, but for searching for scientifically meaningful connections within geoscientific data. And in this work, they show application on two quite simple problems on Earth system variability. They separately train fully connected neural networks of identical architecture separately for each of the tasks, and the network has an input layer which receives vectorized maps of geospatial phenomena, two hidden layers with eight nodes each of them, and an output layer is represented by two nodes, two unit vector that describes which of categories image is associated with. And let's look closer into interpretation algorithms. First method calls backward optimization, and it has a more fancy name, fancy title, optimal input. First, we need to train the network and freeze its weights and biases so they are not going to change through the optimization process. Then we identify a desired output. In case of classifiers, the desired output could be when the neural network is 100% confident that the input belongs in one of two categories. And then we need to generate all zeros input. This is the vector with all zeros elements. Then we pass it through the network, get the output, and calculate loss for the received output and previously defined desired output. The next step is propagating the loss through frozen weights to update the input, and we repeat these iterations with updated input vector until the loss covers and gets equals to 0. And as a result, we get an optimal input vector which has the same dimensions and represent the same physical quantity as the samples we use to train the network. And the optimal input shows how the phenomena map would look like to be labeled as one of two categories we have chosen. For the layerwise relevance propagation, we again use trained network with frozen weights and biases, but in this case, there is no need to generate any input vector, zero input vector, because we are going to use a sample of our interest as an input, and we pass this sample through the frozen network and retain the output. The output is starting, the output value is a starting relevance at the output node which we have chosen to propagate backward. And usually this node is the node with the highest likelihood. Then we propagate relevance from the output node to the previous layer by using the propagation rule until we reach the last hidden layer. And this choice of a rule depends on the type of the neural network input data and what type of information is that we are going to get from the network as an output. And this rule on this slide basically just makes the all nodes with negative weights transparent during the propagation process. And the last step is to propagate relevance from the last hidden layer to the input layer. And here they use a different rule which ignores all biases. And this rule depends on whether the values of the input feature are bounded or unbounded. And like overall, for this method, we use a sample of our interest of as an input and a specific set of propagation rules, and the result values have the same dimension as the input and correspond to the relevance of each input feature for the neural network decision. And now let's move to the most interesting part of the article. These are examples. And for the first example, shows how methods can be used to interpret neural networks understanding of the spatial structure of a well-known climate pattern, the ANSO pattern. The ANSO pattern is an ocean atmospheric pattern which has a strong influence on the weather conditions in North America. And it has two phases. The positive one, El-Nino, when the relatively warmer seawater stays closer to the east coast of South America, that reduce the upwelling, so we have the positive anomalies. And the negative phase, La Nina, when the trade winds are strong enough to move warm surface water towards Asia, and it increases intensity of the upwelling, and this creates negative anomalies. And this example is intentionally simple, so it gives us the opportunity to test the abilities of the interpretation techniques. And they train a neural network with the architecture I already described in the beginning to predict the phase of ANSO pattern by using a set of SST maps and phase labels. Besides, they use already, I would say, classical linear regression approach for this task, just to check if the interpretation gives really physically meaningful insights, or if our neural network just have a very good imagination. I'm going to show application only for El-Nino, but the technique could be used to analyze La Nina as well, and you can find it as the supportive materials for the publication. And the results of the interpretation are extremely interesting.
Vadim, can I interrupt with a quick question? Am I understanding the task right? The idea here is not to predict the phase of the oscillation in the future, but rather to just take an image and say, what is the phase right now?
Yeah.
Okay. And the reason it's such a simple problem is to test if the result makes sense, because you know what you would expect to see.
Yeah.
Okay, thanks.
Exactly. Oops. Yeah. And as we see, optimal input recovers a map of SST anomalies that is very similar to observed answer pattern. And we can see that the composite observations has similar spatial structure and magnitude within tropical Pacific region. And they still have some differences in a sign and magnitude outside the tropical Pacific, especially in the, for example, Atlantic Ocean. But these regions are not considered to be a part of ANSO, and either they're not highlighted to be important for the labeling by the layerwise propagation relevance composite map. And this composite relevance map for El-Nino samples also shows that the neural network mainly focused its attention on the tropical Pacific region. Besides, there exists a region of non-zero relevance. Maybe it's not seen on other screens, but it is here. And so non-zero relevance, and it's within the non-specific region, and it can be associated with a well-known correlation between oceanic variability within this region and the tropical signal of ANSO. And if we look at the linear regression approach, this coefficients map, they are spatially like the optimal input pattern. So these increase confidence in the robustness of the neural network visualization methods because they give quite the same results. And if you look at heat maps for individual samples, we can say that layer-wise propagation method show more insights, show not more, some insights which we couldn't get without the this interpretation of this neural network. And the network refocuses its attention on different regions of the tropical Pacific to identify an El-Nino event depending on the input. And furthermore, the neural network focuses its attention on the regions of SST anomalies that are most associated with two types of El-Nino and learns to ignore other anomalies, even if they have similar magnitude within the Western Pacific. And we can see that for the East Pacific El-Nino sample, it focuses on the east part of the tropical Pacific region, when in case of the Central Pacific El-Nino samples, its focus is moved to the central part of the region. In addition, the relevance time series for the Central and Eastern Pacific show that the network correctly refocuses its attention for all the input samples depending on the type of El-Nino event. And so samples associated with Central Pacific El-Nino, this is the letter C, have higher relevance within the Central Pacific than within the Eastern Pacific, and vice versa for the samples associated with the Eastern Pacific El-Nino. To further illustrate the usefulness of the interpretation methods, they extend the usage to a slightly more complex example. In this example, the network is trained to predict a surface temperature response, basically just design in the response to SST anomalies months in advance. And the focus here is on seasonal prediction, for which the ocean is the predominant source of atmospheric predictability. And it's well known that answer as well as the Pacific, North Pacific region are dominant contributors to atmospheric seasonal predictability, and they can impact surface temperature and even precipitations across North America. And let's look what the interpretation can show us in this case. Here they use interpretations of the neural network to identify which SST patterns are useful for making extended surface temperature prediction at various prediction lead times. First, a neural network is trained to predict the sign of the 30 to 90 days average sea temperature anomalies. It's 60 days lead. And for this time lead, the optimal input and LRP composite identifies similar regions on SST patterns that lead predictability across the tropical and North Pacific regions. And both of these regions have been identified by previous studies as sources of seasonal temperature predictability for the west coast of the North America. And next results are going to be even more interesting. To test the correctness of the neural network interpretations, they vary the prediction lead time of the continental surface temperature anomalies from 180 days to 60 days, 180 days prior to 60 days following the occurrence. And the same as for the previous task when they was identifying phase of the answer phase, they compare results of the neural network interpretations with results of linear regression approach to test whether the interpretations are reliable and if they offer any unique insights compared to the more conventional approaches. At extended leads, the spatial patterns of SST anomalies identified by two methods are similar to those identified by the linear regression method. And particularly, the tropical Pacific stands out as being a predominant source of surface temperature predictability across 180, 120, and 60 days prediction lead times for both the neural network and the linear regression maps. For the 60
Vadim, I'm
days
sorry, can I interrupt one more time?
Yeah.
I'm struggling to understand what these
Yeah.
networks are doing. They're very small networks again, right? You only have 2 layers of
Yeah.
8 nodes. So, and they're predicting into the future now, right? They're doing a seasonal prediction.
Yeah.
But what are the inputs and the outputs are both for the same grid point? Is that correct?
Sorry, can you repeat again?
The inputs and the outputs are, you have one input for every grid point, huh?
You have one node for one grid point, so
Oh,
input
okay.
layer
I
has the
see.
same
I
amount.
see.
Like
I
it's a
see.
vectorized map, as I said in the beginning. But
I apologize. Yeah, okay, so you explained
Yeah.
that. So basically, they're learning basically 8 modes or components in some nonlinear way that depend on the entire
Yeah.
map. Okay. All right.
Yeah.
Thanks.
yeah, I think I should repeat this, but yeah, sorry. Okay, and for this 60 days prediction lead time, within the neural network interpretation, the importance of the North Pacific region begins to increase relatively to the answer region. And the North Pacific becomes the dominant source of predictability for the concurrent and 60 days lagged SST anomalies. Actually, this experiment for me is the most strange one. But yeah, and for these lead times, the regression approach still continues highlight the tropical Pacific Ocean as important for identifying the surface temperature anomalies, and the neural network doesn't. This is the, I would say, the only like strong difference between these approaches, but at the same time, neural network is more confident with the result than the linear regression approach. And I would say these are exciting results, and these techniques for interpreting neural networks have a huge potential to be extended to the discovery of unknown patterns within geoscientific data. In the conclusions of the article, they say that these concepts will be further explored in future research. So I'm very excited of this article, and I would follow the research. I think that's all for my presentation. And from my side, I would like to say thank you very much for your attention and for your participation in, oh yeah, this is the anniversary ML seminar at Hereon. And yeah, David, catch the flow.
Thanks a lot, Vadim. That was a very nice presentation. Have we got questions? I have one or two, but I'd like to hear from everyone else first. Oh, we have a couple questions. So Eduardo, do you want to go first?
Okay. Well, thank you very much for the explanation of this paper. It seems that all these algorithms are focused on neural networks. And my general question would be, is there anything similar for other type of machine learning algorithms? Like, let's say, decision trees or
yeah, actually, yeah, there are some different methods that you can use to interpret different machine learning algorithms. And actually, we was deciding on the second paper, which is exactly shows methods for all kind of machine learning algorithms. And this one, but this one was more close for me because I don't have background in atmosphere. But we can share the paper. There are lots of explanation about these methods you can use.
Could someone or you or someone post this second paper in the chat so that we can make and have a look at it?
Yeah, we'll do that. We'll try to put it on the seminar website as well.
Okay. Thank you.
Kubi, you had a question.
Yeah, can you hear me?
Yeah.
Yeah.
Okay, perfect. So my question was, how did they, I think you actually mentioned this, but how did they check that the relevance doesn't just correlate with like the amplitude of the signal at a certain point? Because I mean, clearly in these signals, the El-Nino signal is very strong, but there were also other places where it was, let's say, I don't know, maybe half the amplitude. And then you could also see that there are also some signals of relevance. So is there one clear test that shows that even if the other ones would have the same or higher amplitude, you would still have more relevance in these areas?
Well, basically, these relevance maps are composite maps for all samples for El-Nino and yeah, well, not this one for El-Nino, this one. So they, this is not only one experiment. This is kind of composite map of all experiences, or like experiments with all samples.
Yeah, so the question would be, is there one case where it's, for example, very difficult to tell what's relevant because, for example, in other areas, there's also a strong signal, and there they show maybe that still they have a bigger signal at the place where the surface temperature anomaly is? Or do they not have anything like that? Because that would be my first question, if I wanted to be critical about this.
I think they didn't have something like this. And the old pictures here was like the old pictures shown here was more like concrete. So there wasn't any like, for example, for this picture, there is exactly this pattern that should be here. And for the second one, there is exactly like it highlights exactly these patterns. So I don't know. I haven't seen anywhere, even at the supportive materials, some other pictures beside this. So.
Okay, thanks. No, that was just the question.
So I have a question. Like, Why is this layerwise relevance propagation the way it is? I just don't get it. What is up with only looking at positive weights and biases? What's the logic for this? I don't understand it.
Mm,
We didn't talk too much about the tech.
That's
Yeah.
that's an interesting question, actually. But I'm not sure that I really can explain this.
Yeah. I mean, this is
Mm,
reference Bach 2015.
yeah,
I haven't read this, and maybe this might be an explanation. I mean, intuitively, there's something appealing about it, right? Like we want to say which inputs are relevant for increasingly output in one category, but you have multiple layers, and what might cause a decrease in one layer might cause an increase in the next layer if you have two negative weights in a row. So it's not obvious to me why you should just. It's very funny because I look at the activations calculated through with all the weights, but then they kind of do a back propagation step with those activations and only the positive weights and biases. I'm sure there's some reasonable intuition why you want to do this, and clearly it gives you these very nice narrow stripes, which make a lot more physical sense for something like El-Nino, but I don't really understand why it works. So maybe we need some method to help interpret the interpretability method.
If I quickly may add something, so
Maybe somebody else has an insight there. I don't know.
can you hear me? Okay.
Any other questions? I have one more question, but I'll.
If I may quickly chime in,
Yeah.
just rereading the paragraph from today's paper on layerwise relevant propagation, it seems that the exact algorithm for the relevance propagation has to kind of match the network architecture, which makes a lot of sense. And what you don't see much on the slide that Vadim currently has open is the nonlinearities of the network, right? It's not only the weights and the biases. And I think that the thing with only looking at the positive weights comes from the fact that they're having ReLUs. And it seems to be trying to approximate the fact that they're having this ReLU nonlinearity, at least accounting for it, even though just from the text it doesn't sound like it's perfect. So this type of relevance propagation algorithm, the authors of today's paper seem to write, is something that has come up to work in practice and is heavily inspired by the ReLUs.
Yeah, I mean, I can see that you want to do this with ReLUs. You wouldn't do this with, say, hyperbolic tangent activations or something like that. But okay, I still don't have an intuition why this is the right thing to do. And I'd like to know what is being approximated by what. Apparently, there's a connection to Taylor expansion of the function represented by the neural network. Maybe if you look at all the math, it makes sense. So we just have to do that at some point if we want to understand this. Yeah. Interesting. Okay. The other question I had was about the optimal inputs, and this is more just speculation, but so they say one of the limitations is you really only get one optimal input. Okay, maybe you can initialize with true inputs that it was trained on or tested on and see where that gets optimized to instead of the zero initialization. But in the end, you end up with just one answer. I wonder if it would be possible to extend this in such a way that we get an ensemble of inputs, which all sort of produce high value for some output. Maybe a bunch of different local minima, or just kind of an ensemble that represent a region of input space, which gives you a high output for one of the outputs. I wonder if this is possible. It seems to connect to other ideas from machine learning, like variational inference, and also from Bayesian statistics like Markov chain Monte Carlo we haven't covered too much. I wonder if anyone's doing this to try to represent these regions of input. Okay, well, that's my idle speculation.
As a direct response to this, I mean, the loss is not a likelihood, even though you could make it one.
Right.
But there are some connections between stochastic gradient descent and some form of Bayesian inference. Like you take how much does the optimized value bump around as you do mini batch gradients as an indication for uncertainty, at least around the optimum?
That would be one thing. Yeah. You could also think of it as an energy model on the input, right? Like if you have, let's say you have like two output classes, like El-Nino and La Nina, and you take the log probability of El-Nino, and then you use that as an energy function on your input, that kind of defines a probability distribution. You can try to sample from that. I don't know whether that's a sensible thing to do, but maybe it'll give you a bit of a sense of how diverse the inputs are, which could produce this output. All right.
I would have one more, I don't know, comment / question. That goes back to the network architecture that they picked, which, if I understand it correctly, is you have these in the
So you're coming through very quietly.
Okay, sorry. Maybe this is a bit better.
Much better.
Okay, sorry for this. So you have these 8 nodes in the first hidden layer, and they have as many input weights as you have grid points, right? So from just the figures, it looks like a couple hundred. So one thing that would have been maybe interesting to look at is just like, what are these maps of these first filter bank? What do they look like? Like, what kind of features do these 8 nodes represent? Because that's a bottleneck. You reduce the entire input image to these 8 numbers, and then you check, right? I mean, how do they relate in the second hidden layer and the output layer weights? But just which features does this pick out? Maybe you have to untangle them, do some ICA on the activities because these maps may be linearly mixed among those 8. But it would have been interesting to just look at what do these filters actually look like. Just the input filters, like the weights of the first layer. And they don't do that, right? They don't have that, neither in the appendix nor elsewhere. Or did I overlook it?
I think they don't.
Like when people train convolutional neural networks on image data sets, one thing that people like to do, at least in the beginning, is like look at the filters. Like often you get stuff which you also have in the human visual system, like edge detectors and contrast relevant filters. It would be interesting to see if none of those 8 filter in the first layer, if none of those have any weight, say over Europe or something. And what do they then actually look at? What features over the Pacific?
Yeah, these small networks make a lot of sense because we're so data poor and there's seasonal prediction problems. There just haven't been that many years since we've started getting the data.
I mean, convolutional networks where you have aggressive pooling and then you have a bunch of layers that each time shrink the input domain by a factor of 4 in each direction, probably wouldn't have much more, might even have less weights in total than this network, right? Because this network has at least 8 times as many as you have input grids, just from the first layer. But a convolutional neural network just has, if you have few filters, and if you have 8 filters on the first layer, you retain as much information. Might not have many more networks to train. And I think all of the algorithms that they presented here would also work for CNNs. The optimal input for sure, because CNNs are also differentiable with respect to the input. And also I think the layerwise relevance propagation you could probably use right away, because you can write fixed CNNs in particular with fixed weights as fully connected networks and apply the algorithm now. Yeah, so I guess what I'm saying is one could easily redo all of this with CNNs without needing a lot more data probably. But it might not have been as straightforward to explain with these actually really nice figures that they have than with just feed-forward neural networks.
Yeah. Yeah, I wonder if this will eventually become kind of a standard thing that you do in every machine learning paper, you know, just as you might explore different learning rates or network architecture sizes, maybe at some point it'll be expected that you do some very basic interpretability analysis. But so far it seems to be a rather niche thing, a set of papers to explore this aside from everything else. Occasionally you see sensitivity analysis, like we saw this in the weather bench paper. But I wonder if this will become more common. It would probably not be a bad thing.
I mean, one thing that is in this paper that might be nice to become a lot more common for a lot of machine learning papers is just to include a linear model as a baseline.
Yeah. That's true. Okay, any more questions? All right, so thanks again to Vadim. Nice presentation. And we will see you again in 2 weeks. Bye-bye.
Thank you.